Hi there, this is Miss Andersen. Today we're going to look at optimization using quadratic functions. So by the end of this lesson, you should be able to understand and apply optimization of those functions. First, I'd like to review some important facts about quadratics. So quadratics, and if you could pause the video and kind of quiz yourself on this first, that would be great. But I'm just going to go through the answers here, so feel free to pause and then play again. Quadratics will always include an x squared. Quadratic, a parabola, has to include an x squared. Any quadratic can be written in standard form, and this form looks like ax squared plus bx plus c. The axis of symmetry in standard form is a vertical line, so it's x equals negative b over 2a. That's in standard form. And the vertex, of course, is going to be negative b over 2a and f of negative b over 2a. So it's going to be the same x value as the axis of symmetry, and then to get the y value, plug it back into the original function in standard form. Negative b over 2a goes in for x. Any quadratic can be written in vertex form, which is a times x plus h squared plus k. The axis of symmetry in vertex form is x equals negative h. The vertex in vertex form is negative h comma k. And the graph of a quadratic will always form a parabola. Okay, if we want to find the maximum or minimum of a parabola, and it happens to be in standard form, the maximum or minimum will occur at the vertex, of course. And so if it's in standard form, it's going to be negative b over 2a. X equals negative b over 2a. If we need to find the maximum or minimum value of the function, we just plug this value of x back into the original function and substitute it for those x's. So we'll look at 4 examples of that. So you've got 40 meters of fencing, and you want to optimize the total area that you can fence in with this 40 meters of fencing. And you don't put a fence on the house side. So here's a picture of our fencing. It's rectangular, so we can call the smaller sides of the fencing x. We could call the longer side y, and we're not going to have any fencing here. So if we only have 40 meters of fencing to work with, we know that if we add up our x plus y plus x, or in other words, 2x plus y, that's going to give us 40 meters. We want to optimize the total area. Okay, so of course we're going to need an equation for area, and optimize means maximize. We want to make the area as large as it can possibly be. So if you think about it, this rectangle is going to have an area of x times y, length times width. And we've got 3 variables here. We've got a, x, and y. And that's one too many to work with. So we have to use the previous equation that we created, this 2x plus y equals 40. And we can solve for one of those variables and then substitute it into our area equation, which is the one that we want to maximize, because we want area to be the maximum. So the easiest one to solve for is y, because it doesn't have a coefficient. So y equals 40 minus 2x. And we can substitute that in here. So we've got an area of x times 40 minus 2x. So that's what we want to optimize. If we multiply that out, we've got negative 2x squared plus 40x plus 0. So that's in standard form. What should the dimensions of the garden be? So in other words, what is x? And what is y? So to find x, when it's the maximum, we're basically looking for the vertex. We know that A is negative, so this parabola is going to be opening downwards, and the vertex is going to give us the maximum. So to do that, we can do negative B over 2A, and that will give us the x value at our maximum, the x value of our vertex. So negative 40 over negative 4, and that's going to be 10. So x equals 10 meters. And y, of course, we can substitute that 10 back into the equation that's already solved for y. So y would be 40 minus 2 times 10, which is 20. So 40 minus 20, y equals 20. Another way to do this is to graph it. So we can graph the equation that we created. We can graph it factored, or we can graph it in standard form, but we're graphing the area function. So we can put in x times the quantity 40 minus 2x, and we can zoom in a little bit. You can go to zoom fit, that's usually a good one, and we can then analyze our graph and find the maximum. You click to the left of the maximum for the lower bound, to the right for the upper bound, and it gives us a maximum of 10, 200. So again, x is equal to 10. Okay, we found that. The 200 stands for A, so our maximum area is actually 200. And you can see that because area is x times y, we found y to be 20, so 10 times 20 would give us a maximum area of 200. So in answer to the question, what dimensions should the house be, or sorry, should the garden be? Well, it should be 10 meters by 20 meters. X is 10, y is 20. So 10 meters by 20 meters. Of course, the graphing method, you get x, so then to get y, I think the quickest thing to do is just to plug that value of 10 back into the y equals equation. Okay, next example, we're given a profit function of skis, and we want to find the maximum profit. So this is already in standard form. We're already given the function itself. So we can even call that y. Okay, so we want, again, A is negative. So we know this parabola is going to be opening downwards, and the vertex is going to be the maximum. So if we're looking for the maximum profit, we're looking for the y value, because this function is equal to the profit. We could call that p of x, if that makes more sense. So we're looking for this value. So in the coordinates of the vertex, we actually want f of negative b over 2a. We want the y value of the vertex. So to find the x value, we'll have to do negative b over 2a. So negative 3 is our b over 2 times this. We can quickly calculate that. And we get 15,000. Okay, so x is 15,000, but we want to know the profit. We want to know y. So we can plug x back into our original function. So we can find p of 15,000. We'll do negative 0.0001 times 15,000 squared plus 3 times 15,000 plus, oh no, minus 12500. And we can calculate that. And that gives us 10,000. So the maximum profit, it doesn't give us the currency, but is 10,000. According to this profit function. We could also graph it, of course. So we could plug in the function and again, fit's a good one, and then you can just continue to zoom out until you can see your maximum. Okay, and you can go to Analyze Graph, Maximum. And this way you don't even need to do any calculations other than converting from scientific notation. So it gives us 1.5 times 10 to the 4th is our x value. So 15,000 when we do 1.5 times 10 to the 4th. It's going to move our decimal 1, 2, 3, 4. So 15,000. And then it gives our profit right away. It gives our y value right away. We don't even have to calculate anything other than convert that from scientific notation into normal notation. So we'll have 1 times 10 to the 4th or 10,000. So either method works. It's good that you're able to do both, though. Okay, so we've got a baseball tossed into the air at 15 feet per second. We're given the corresponding function of motion, and we want to know what's the maximum height the baseball reaches. So again, a is negative. You can see our coefficient of t-squared is negative. So we know this parabola is going to be opening downwards. We know that the vertex is going to give us a maximum. So if we want to find the x value of the vertex, let's think about what that's going to give us. T, the variable t represents time in this function. And the idea that it's 15 feet per second, we know that that time is in seconds. Okay, if we want to know the maximum height, well, that's S of t. S of t stands for the height. So we want to know the maximum value of this function. Again, we're looking for the y value. So in this vertex, it's the y value that we're trying to find. So if we want to find the x value, first of all, or t in this case, we can do negative b, negative 15 over 2 times negative 16. And we can calculate that. Oh. Okay, so about 4.69. Or sorry, 0.469 seconds. And we want to know what height does this baseball reach in 0.469 seconds. So we can plug that value back into the original function. So we'll do f of, or actually t of, no, s of 0.469. So negative 16 times 0.469 squared plus 15 times 0.469 plus 4. And again, we can calculate that. So negative it's a good idea not to just use the rounded value, 0.469, but to use the most accurate value you can. So like 0.46875 is much better than to put in your rounded value because it could affect your solution too early. Okay, and we get a value of 7.5 about 2. And in these examples, 3 significant figures is pretty good. It depends what you think is appropriate to round to. Maybe if we're talking about feet per second, it's nice to say, well, it's about 7.5 feet that this ball was tossed in there. This is the maximum height it reached. Okay, another way to solve this, we can of course graph our function. So negative 16 x squared plus 15 x plus 4. If we go to zoom fit, we can see that our vertex is very, very close to the origin. So it makes sense that it's not in the air very long, this baseball. If you toss something in the air, it really doesn't stay in the air very long. So it makes sense that those seconds are close to 0. It's not very long before the ball will reach its maximum. Okay, we can analyze the graph, finding the maximum. And again, it gives us this information really quickly. So the time that the ball will reach the maximum is at 0.469, and the maximum it'll reach is about 7.52. And that's what we got to when we calculated it. So again, either method is great. It's good if you can do both, ideally. So it just gives you more options to work with. Okay, last one. There are 60 apartments in Allen-Minden that can be rented for 600 Swiss francs a month. For each increase of 50 Swiss francs, 3 tenants are lost. So every time the owner increases the apartments by 50 francs, 3 renters don't want to rent there anymore. So we want to know how much should the rent be so that the revenue is at the maximum for whoever owns these apartments. So we want to maximize revenue. Revenue, of course, is going to be the price of the apartments, the price of rent, the cost of rent. And that's going to be multiplied by the number of apartments rented. Okay, so revenue, the amount gained for whoever is renting these apartments is going to be the price that each apartment costs times the number of apartments rented. Okay, so we have the lowest they can be rented for is 900 Swiss francs a month as far as the price goes. And for each increase of 50 Swiss francs, 3 tenants are lost. Okay, so the number of apartments that we have to rent are 60 apartments. So let's call each increase something. So let's call this X. And we'll call it the number of increases. Okay, so just so you can see how that works, if x is the number of increases, that means when x equals 1, we'll have an increase of 50 Swiss francs. The total rent will be 950, and we'll lose 3 tenants. 3 times 1 gives us a loss of 3, so we'll have 57 tenants then. Okay, so back to our price of rent. Price of rent is going to be 900 francs plus 50 times the amount of increases. So if there's 0 increase, the rent is 900 francs. The number of apartments rented, well, we're going to lose 3 for each increase. Okay, so we've got our quadratic function. Notice that when we multiply this out, when we FOIL this, the coefficient of x squared, when we multiply those two values, is going to be negative. So again, we've got an a that's negative. Our parabola is going to be opening downwards. And we want to know how much should the rent be so that the revenue is a maximum. So our revenue is going to be maximized at the vertex of that parabola because a is negative, because the parabola is opening downwards. Okay, so we want to know how much should we charge for rent. In order to find that, so basically we want to know this value, 900 plus 50x. So we need to know x. So we could multiply this all out. I think really the fastest method is to just graph it. So you could, of course, you could multiply these values out. You could FOIL them. You could get your quadratic function in standard form, and you could do negative b over 2a to find x. Or you could just simply enter it in as your function of your graph. Okay. Just gonna zoom in a little. Okay. Anyhow, so we can see that our maximum is going to be when x equals 1. It's right away. And then it gives us what the actual revenue is at that point. So we've got 1 comma 5.41 times 10 to the 4th. So all we care about is what is x. Well, x is 1 when our function is maximized. So x equals 1 when we have a maximum revenue. And the question is, what should the rent be? How much should rent be so that the revenue is at a maximum? Well, rent is, again, this value. It's 900 plus the number of increases that we've done. We've done 1 increase to maximize it. So rent should be 950 francs to maximize our revenue. Great. Thanks, guys.